Hi, I hope everyone's got lunch by now and are ready for the afternoon sessions here in the big room. Everyone here who's been doing Java development at some significant scale has probably been across the problem of modules, like jars in nested jars of jars, or stuff like that, or trying to separate class loaders and stuff. Been on several attempts going down the way of OSGI, etc. And it seems like there's some light that will shine on the horizon. So I've got the honor to introduce a guy who actually came across the first time in a ski lodge some 10 or 12 years ago at the summit named the Colorado Software Summit. And since then, it's been one of my fixed stars on the Java in the Java field. So I'm really thrilled to hear what's coming up in Java 9. So Mark Reynolds.
Thanks very much, Dan. It's great to be back here at JFocus. So this is a talk about Java 9 and in particular the premier feature. What we see is the premier feature of Java 9, which is modules. So if you saw my talk last year, this is an update on that. Hopefully there should be some new material here. So why are we doing this? What is this all about? Well, the JDK historically has been this monolith, right? And it's not just the JDK, but frankly, every implementation of the Java SE platform has been this huge, enormous, indivisible thing. And, well, this is a problem. It's a problem for small devices, for example. You know, lots of embedded devices have a processor that's perfectly capable of running an SE class VM, but maybe not so much memory, and it's hard to fit all 50, 60, however many megabytes of a full Java runtime environment on a device like that. Believe it or not, it's also a problem for big devices. In cloud deployments, people are really motivated to reduce costs by putting as many different virtual machines, containers, whatever technology it is that you're using on a big machine. Just because you have a big machine doesn't mean that you want to waste a lot of space on it. So wouldn't it be great if a server application only needed parts of the JRE, you could just deploy parts of the JRE rather than the entire thing. Now in Java 8, we made some headway on this problem with the introduction of compact profiles. Compact profiles were sort of a down payment on modularity, or in another way, they're sort of a very poor man's module system. What we did was we carved the platform up into concentric layers, kind of like an onion. So if you look at the full JRE, it's 55 megabytes. If you look at a Linux ARM32 build, we introduced a core layer called Compact 1, which weighs in at just 11 megabytes. It doesn't have a lot in it, although maybe more than you think. It's got about a bit over 2,000 classes in it. All of the core things, java.lang, java.net, java.util, java.io, NIO, some very, very basic stuff. But it doesn't have XML support or JDBC or Corba or other extra things. Around that, there's Compact 2, which adds a bit more stuff and costs, another 6 megabytes if you want to carry that around. And then Compact 3 is 30 megabytes. Compact 3 is just about everything except the desktop. So if you have an application that's not using Swing, AWT, or 2D, or Beans, the Beans introspection stuff, which sadly is deeply in bed with all that, then Compact 3 will actually probably do the trick. Okay, so that's where we went so far. But the thing is, compact profiles, they help, but they're not. They're just sort of an okay solution. They're not a great solution. If you have an application that needs just one package from Compact 3 and otherwise is content with Compact 1, then, well, gee, now you have to carry around 30 megs when 11 and a little bit would have done the trick. All right, another category of problems we're trying to attack with all this is that of performance. Because the JRE is big, because the JDK has evolved over the years as a monolithic system, there are lots of interconnections that make the startup of the system fairly slow. There are also things we would like to do for performance, such as ahead-of-time compilation and aggressive inlining, that are tricky to do without a module system. Having a module system really helps and provides a natural point in the development cycle at which to apply those kinds of techniques. A third category of things, a category of problems we're trying to attack is security. As you probably know, over the past few years, Java security has, been in the news more than we would have liked. Engineers at Oracle and elsewhere have done a lot of work in the past few years to get the security backlog down, address all of the critical issues, and that's been successful. But we don't want to stop there. We want to keep making the platform and its implementations, ever more secure. A particular issue, which we think we can address with modularity, is this one. Well, let me explain what I mean. If you look at the JRE, there are lots and lots of API packages. Many of them, especially the ones that start with Java or JavaX, are actually meant to be used by external code. They are so strongly meant to be used by external code. They're part of the Java SE platform specification, and they're reviewed and approved in the JCP and so forth. There are a few others that are provided as kind of implementation APIs. They're part of the JDK, but it's okay for external code to use them. And then there are a whole lot, everything that starts with Sun, and some others that are only meant for internal use. Yet, code in there is actually visible to external code, and external code can use it. And if we didn't do anything about it, then a malicious Java applet could be loaded and go, groveling into Sun misc unsafe or sun.reflect something and do all kinds of bad things. So how do we prevent that? Well, since Java 1.0, we've had a mechanism in the security manager. There's this method called check package access. What check package access does is it looks at the thread that invoked it, looks at the prevailing security context and makes a decision. Well, is the external class that's on this thread in the present security context allowed? Is it permitted to access the code in this package? And so if an unprivileged applet asks to get to Sun misc unsafe, of course it will say no. So getting check package access to return the correct answer isn't that difficult. What is difficult is making sure that check package access is invoked throughout the entire platform at all the right times. So this is a fairly brittle mechanism. If you miss just one point, then that could be a security vulnerability, and indeed, several of the more serious security vulnerabilities have been traced. The root cause has been a missed call, a missed check of check package access. So, this is something that we want to do a better job of. Related to that is even if you aren't running completely untrusted code from some random site on the net, it's a problem for those of us who maintain the JDK that people use all these internal things, right? Not just Sun misc unsafe, but even really seemingly innocuous things. Sun misc base 64 decoder. Well, arguably we should have put that into the platform years ago. We finally did that in 8, but over time, we want the ability to get rid of a bunch of these internal APIs. There are quite a few of them that actually serve no purpose except to keep external libraries running. And there are some like stuff in Sun misc, sun.reflect that we'd really rather not have people tampering with unless they're willing to go do deep reflection to do it. So we want to make these inaccessible, not just to improve security, but also to make it easier to maintain this large platform, which is like 6 or 7 million lines of non-commented code. Now, if we're going to modularize the platform, we'll have to build a module system. And if we build a module system, then conveniently we can solve another problem, which is helping everybody, not just people who work in the JDK, escape from class path hell. Right? The class path is this mechanism that's been around for years. It's fairly primitive. I think pretty much everybody understands the issues of the class path. Many times I've seen large applications with difficult to diagnose failures where the root cause winds up being, oh, well, you had 3 different versions of some logging jar on your class path. and it was pulling classes from one of them and the other one, and sometimes even the other one, depending on search order and whatnot. And well, yes, of course, things were confused. So there's the multiple version problem. There's the missing library problem. If you forget to put a jar on the class path, your application could run fine, until at some point somebody invokes some code path in your application that required that jar that, oh, now it's not there, and you have an error in the field. That's no fun. And of course, another problem with the class path is, just like in the JDK, there's no way to hide your internals. You can't ship a library and say, well, the APIs in these packages I expect people to use, and the APIs in these packages are internal, and I don't want people to use them because I want to be able to evolve them over time. There's no way to do that. So we'd like to solve that problem too with a coherent module system that addresses both the needs of modularizing the platform and the needs for everybody, developers everywhere, to eventually migrate to modular systems with true modules rather than jar files, which are just sort of hacked up zip files and with no encapsulation. Okay, so let's get rid of the class path. Okay, we've got this monolithic thing. What we want is this, right? We want a box of Legos, a box of parts that you can plug together in all the right ways, such that you only need you only wind up having to carry around the ones that you actually need. So this is what we've been doing in Project Jigsaw. This project has been running for a while now. It actually, believe it or not, started in 2008, and we've been working on it more or less continuously since then. Jigsaw is a large project. It's making major changes to the Java runtime system and to the APIs. It consists of four JEPs and one whole JSR. So JEPs, I should say, if you're not familiar with how we do all this work in OpenJDK, a JEP is a feature unit. It's a unit of describing a feature and tracking work on its progress. So it's more about implementation really than specification, although it does include design and can have specification material in it. So for JEPs, the first defines the modular structure of the JDK. In the second one, we restructured all the source code in the JDK source tree to be in a modular form. In the third one, we modularized the runtime images, and in the fourth one, we will actually introduce the module system that will be specified in JSR 376, which was approved last December. Okay, so the modular JDK. Let me give you an idea of the work that was required here. When we first started trying to modularize this big monolithic code base, it was pretty tough since it had never been designed with modules in mind. This is what it looked like when we started. This was our first cut at how to divide it into modules. So the red thing up there, that's the base module. The idea of the base module is that should be the one module that you always have to have. It has the essential things: Java-lang object, Java-lang string, stuff like that. Everything that the language requires is in there, and things that, well, simple applications require. Hello world, for example, is in java.base. So java.base shouldn't depend on any other module. Every other module should depend on java.base, because every other module, at the very least, will need Java-lang object, because that's how the language works. Well, if you look at all these, the edges here are the dependencies that tell you which module needs which other. In our first cut, if you took the transitive closure of java.base, because it actually does depend on some other modules, you got this. So this was not a very successful first attempt. If you just need java.base, then you have to pull in, it looks like about 2/3 of all the rest of it, and including useful things like, JAXP parsers and Corba and management and logging, and well, this makes no sense. So my colleagues Mandy Chung and Alan Bateman have done a lot of work over the last couple of feature releases to prepare for modularization by attacking this diagram and trying to get rid of the red. In many cases, they were able to snip some of these unfortunate dependencies by rejiggering some internal logic, making external connections internal. In a small number of cases, they actually had to change the API. So in Java 8, we deprecated, I think, 8 or 10 methods here and there that were causing dependencies that were extremely unpleasant, and but there was no other way to break them. So there were some obscure methods, for example, in the Java util_jar package that referred into the desktop module that would require the base module to depend on the desktop module. So we deprecated them in 8. Those methods will go away in Java 9. Where we wound up is here. This is the current module graph. Now overlaid on this are the onion layers from the compact profiles. So each compact profile has a module that corresponds to it. So if you have an application that needs Java 8 Compact 2, you can just have it depend on the Compact 2 module, and it will get all of the functionality that is in Compact 2 and Java 8. So there's a forwards compatibility story for people who use the compact profiles in 8. So let me explain a bit about this diagram. So base is at the bottom. That's the base module. Everything depends on the base module. Even if a module doesn't say that it depends on the base module, it will depend on the base module. It's mandatory. Orange modules are modules that will be part of the Java 9, the official Java SE 9 platform specification. So the platform spec going forward will include the names of the standard modules and the API dependencies amongst them. So all of the orange modules will be in the platform spec, and all of the blue edges amongst them will be in the platform spec. So the difference between a blue edge and a gray edge is a blue edge means that a module A is depending on module B because module A's API uses types that are in module B. So in order just to use module A, you also have to have module B. A gray edge means that code in module A, say compiler, internally in its implementation refers to APIs in the logging module. Now it doesn't re-export those to any clients, but it still makes use of them. So you still need logging in order to have compiler, but in terms of the specification, it doesn't really matter that compiler is using logging. It just happens to be doing that. So if someday the compiler module weren't using logging, you could drop that gray edge and it wouldn't affect the spec because the spec only contains the orange edges. So we've got Compact 1, base, logging and scripting. Compact 2 adds XML parsing, the DOM SACs, and streaming APIs. Basic JDBC support, remote method invocation. Compact 3, you get some more, you get XML crypto, prefs, compiler, some security stuff, instrumentation, more SQL, and some other security things. The outer layer, that's the full JRE, so that there's this SE module that pulls together everything that's in the official SE platform spec. And then all this other stuff outside the outermost gray circle, these are the modules that make up the JDK. So going forward, the JDK really is merely just a JRE with some extra modules in it so that you get the tooling and the attach API and the binding compiler and JavaDoc and things like that. All right, so once you've got a nice modular structure, and this is still, well, yeah, it's a little complicated, but we think this is about as simple as it's going to get. What can you do with it? Well, if you have an application that only needs, say, maybe it needs prefs, and maybe it needs Nashorn scripting, and otherwise base is all that it requires, then you pull in the transitive closure of that. So you would get base, you'd get scripting, you'd get Nashorn, you would get the scripting API itself. Prefs, in turn, needs XML. And that's all you would get. That's all you would need. You'd have a much smaller footprint than carrying the entire JRE around. Now, how we do that in practice is with a new tool. We're actually introducing the notion of linking to Java. When I started working on Java in 1996, one of my first questions was, is there a linker like in C? And well, no, there wasn't. Of course, it's more in some ways Java is more like a dynamic language than a pre-compiled language. But we actually have a reason now to introduce a linker, and the notion here is the linker is a tool that will take some number of packaged up modules. And those modules could be modules that make the JDK, they could be library modules, they could be your application modules, and transforms them into a custom JRE image. So you can produce a binary JRE that contains just your application, the libraries it needs, and the JDK modules that it needs, and that's all. You could also theoretically produce some kind of magical JVM image that might even contain might contain everything except the JVM, so it would be even smaller, but can only run on the particular JVM it was created for. So we've got an abstract notion of how we want to create this modular structure. We need a way in which to define it. So let me walk you through a kind of visual description of the concepts we've come up with, and we've been through many rounds of revising this. We wanted to come up with the minimal number of concepts we could for defining modules and the relationships amongst them. All right, so let's start. We have a module called java.base. In that module, there is the java.lang package and some others, but java.lang is the most important one. We have another module, java.sql, the basic JDBC API. It has quite a few packages in it. Amongst them are java.sql and javax.sql. Those contain the exported API that's meant for other code to make use of. So java.sql, like every other module, will depend upon java.base because it needs the stuff in java.lang and a bunch of other stuff as well. If we go to look at some code, for example, the connection interface in the SQL package, it uses java.lang string. Well, that's no great surprise. Where does string come from? It comes from java.lang. Now, if you just go to compile this, it won't work because as things stand in this visual description, the java.lang package is not exported by java.base. So every module description needs to specify which of that module's packages are exported for use by other modules or by legacy code that's just on the class path. So to do that in this visual language, I'll just use an asterisk. So an asterisk on a package means all of the classes and interfaces in this package are exported for any other module or random code on the class path to use. So with that, java.lang string is made available to java.sql, and this code compiles and runs, and it's good. Okay. If we look at java.sql, well, these two packages inside it are meant to be used by outside code. So let's put an asterisk on those. That's good. If we look at some of the implementation code in the SQL module, we see that driver manager, for example, needs to make use of a couple of classes in the sun.reflect package. Now that package, as it happens, is in java.base, but it's not exported by java.base. Now remember what I was saying earlier about check package access? We don't want to make sun.reflect available to everybody. To solve this problem, we just want to make it available to the SQL module. So we do that by exporting it only to the SQL module. So here the sun.reflect package is being exported to java.sql. That will work. But if some other module, even another module part of the JDK, tries to use sun.reflect, it will fail. Okay. There's some other code in the SQL module that uses everybody's favorite logging API, Java util logging logger. There's a method on driver for whatever reason that will return you a parent logger. So the SQL module, since its public types are using types in the logging module, needs to depend on the logging module. The logging module needs to export Java util logging to, well, everybody, because it is a public API meant for broad use. And that will make that work. The logging module, of course, also depends on java.base, and it turns out the logging module also needs sun.reflect. So we can make sun.reflect available to it the same way we made it available to java.sql. Now finally, let's look at an app module. Suppose you've got an app in a module. The package is confu app. The module is just named app. And app depends on base because everything depends on base. App also depends on java.sql. It's going to do some database access. So it gets access to all the types in the SQL and javax.sql packages. Now, suppose app goes and invokes that getParentLogger method. In order for that to work, it will need access to types in Java util logging. So we could say, okay, if you're going to do that, then you've got to be, you've got to be on the ball, or your IDE has to be on the ball and give you the advice that you had better declare that app depends on java.logging. But that would be kind of inconvenient. That would be like saying, oh, well, if you want to do method chaining, then not only do you have to import, the package containing the original class, but you also have to import the packages for every class along the way in that method chain, and that would just be tedious. So instead, what we have is a way of saying a module's definition can say that SQL depends on logging, and oh, by the way, any module that depends on SQL also automatically depends on logging. So it gets all of the logging types and doesn't have to declare another dependence. So that's more of a convenience than a strict requirement, but it's very, very convenient, so we think it's worth having. Finally, there are plenty of other things in the base module. For example, sun.invoke contains a bunch of implementation code for method handles, JSR 292. And it turns out, fortunately, no code outside of the base module needs that, so it just stays there, and it's completely private, and nobody can get to it at compile time or at runtime. All right. There is no gain without pain. Here are some of the changes we've made, more painful, some are more painful than others. The first one is the change to modularize the source code. So this only affects people who work with the JDK source code, but if you ever look at OpenJDK and you've seen the structure in Java, in JDK 8 and JDK 7, the new structure is now very different. We merged this change back last August, whereas source code used to have sort of this schematic layout where there's a source directory and then a shared directory and some OS specific directories, and then a division into classes and native code, and then a division into packages, and then finally Java source files or native source files. We basically inserted another level here, so there's now under source is organized into modules. So you can actually go look at source, java.base, and then all of the source code for the base module, as well as resource files and configuration files and whatnot. So this change, actually, it didn't change the bits that you would get in a JDK build, but it did break everybody's IDEs and everybody's 20-year-old habits of how to find code in the JDK source tree. So that was the first kind of big step. A bigger step was in JEP 220 when we changed the runtime image format. So for many years, the structure of a JRE has looked like this. There's a bin directory, there's a lib directory, and the lib directory has a whole bunch of stuff in it. There are some other top-level directories too, but these are the most important. In the lib directory are a variety of different kinds of files. There are properties and policy files, which are actually meant to be edited by end users, although data indicates that few people actually do, but that's what they're there for. There's the endorsed standards directory, the extensions directory, where you can drop jar files that are treated in certain special ways. There's rt.jar, the jar file that contains all of the runtime classes. And then shared libraries or DLLs for all of the native code that makes up the JRE. We've changed this. This change was merged in December, so if you get the JDK 9 snapshot builds, which we post every week, you will have seen this by now. There's still a bin directory, of course. There's still a lib directory. We moved all the user editable configuration files into a conf directory, so it's very clear. Conf contains things that you can change. The lib directory is still there, but no file in the lib directory is meant to be examined by a user, edited by a user. You should not count upon the existence of any particular file in there. We will change it over time. We got rid of a few things. The endorsed standards mechanism is gone. The extension mechanism is gone. We did a bunch of research which suggested that neither of these were used very much. The endorsed standards mechanism will be replaced by a notion of upgradable modules in 9. RT.jar is gone. Now this, we know, breaks basically every IDE out there and many other kinds of development tools. But we had to get rid of RT.jar, right? Jar files are basically an accidental format. Zip was a convenient format when we needed something in 1997, and it's stuck with us today. But it's a horrible format for execution, for runtime, to be pulling classes out of in an efficient manner. We've optimized that a lot over the years, but we don't think we can push it any further. And especially if you think of techniques like ahead-of-time compilation, well, you might not even have class files at runtime. So why be forced to carry them around? There were some interesting kinds of compatibility issues we had to deal with. Does anybody know what this code does? What does this return? Anybody? Random guess? Whammy? The bytecode? No, it does not return the bytecode. This method actually returns a java.net.url object. And today it would return this, roughly. So that's what's called a jar file URL. The part before the exclamation point is a path in the file system. The part after is the name of an element within the jar file. So this method is actually used. Code that we've found out in the wild will invoke this. Very rarely does that code care what its content is. Very rarely does it care that it's a jar file. But it will go and open it and expect to get the bytes that are in Java line class.class. So we need to keep that working. The way we kept that working was we changed this. It still returns a URL, but we invented a new URI scheme, which we call JRT for Java runtime. So if you have code that was expecting that to be an actual jar file URL, sorry, that will break. But if all you're doing, which is what most people do, is just take that URL and open it and get the content behind it, this will still work. So we have a new URL scheme that's understood. There's a URL handler for it, and all of the other usual stuff that goes with that. Now I said we got rid of rt.jar. We knew that, well, we couldn't just get rid of it and not provide a replacement. IDEs and other development tools do have a legitimate need for exploring the classes that are built into a JRE and being able to get to the actual class files in order to support development. The way we solved that problem is we created a new I/O file system, a virtual file system for accessing the built-in classes and resources. So you can use the new I/O file system API to get this file system whose URI is just jrt:/. Once you've got that, you can use paths within it to get to classes indexed either by module name and then package name, or just by package name, because many legacy applications expect to be able to find things by package name without regard to what module they're in. And the way we do that is there are actually symbolic links from the package index in this virtual file system over to the actual modular part of the tree. So that works fairly well, and we've reached out to all the IDE vendors and other tool vendors to help them learn about this change and offer help when needed for converting tools so that they will work with this new format. Okay, when we conceal the internal classes, when we make the sun.star classes and other internal things inaccessible by default, that is going to break some code. So it would be, if you maintain something, especially if you maintain a library that other people use, it would be really helpful to go use this tool called JDEPS. So we ship this tool called JDEPS. It's actually in JDK 8. If you have 8, JDEPS is in there, and you can run it on an existing jar file or even just random classes. And what it does is it does a static analysis of all of the type references in your code, and can show you which packages and modules in the modular JDK it depends on, and also will note which one of them are internal APIs. And those are problems that you really ought to fix. All right, so that's Project Jigsaw. I'd now like to do a demo. We actually have live code, and we'll see if this works. Before I do the demo, just because I need to, I will show you the obligatory legal notice. Ta-da! Just in case I can't get back to this computer. Okay. Now here's the high-tech part. Boom. Let's just plug this in and scale it. Ooh, there we go. Well, that's most of it. That's enough. Okay, what do we got? Okay, let me just set up here. This is a live build of our prototype. So first thing I'd like to show is the access control stuff. So here's a little test. What does it do? It tries to go use sun.security.x509.x500 name, and that's in one of those Sun packages that's supposed to be inaccessible. Let me run JDEPs on that. I have it already compiled. Here's what JDEPs says. So test1.class is going to depend on java.base. It uses types in java.io, java.lang, and sun.security.x509, which, note, JDK internal API in java.base. So whenever you see one of those, that's something to work on. Let's try running this. Yes. Okay, here's the Java that I've got. Internal build. Classes. Let's run test one. Boom. Okay, I can make this a little narrower so it fits on the screen, I think. A lot narrower. Let me run that again so you can read it. Okay, exception in thread main, illegal access error. So this is the same kind of error you would get if you tried to access a private method or a private field in some class. Class test 1 cannot access Sun Security X509 X500 name in module java.base because it's not exported to the unnamed module. So the unnamed module is a synthetic module. Basically, if you have code on the class path, then it's in the unnamed module. It's kind of by analogy with the unnamed package. If you have a class that's not in any particular package, it's in the unnamed package. Well, if you have a class that's not in any particular module, it's in the unnamed module. All right, so that's a simple test. Let's look at another test. So this one is going to try to get to that same same internal API, but it's going to be sneaky and use reflection. Okay, so JDEPs can't catch this, right? It's only doing static analysis. It doesn't grub the strings and try to detect uses of reflection. So JDEPs won't be able to discover this kind of case. As far as JDEPs is concerned, everything's fine, but at runtime, boom, you will get an illegal access exception. It's an exception in this case because you were using the reflection API rather than the error you get when you're trying to do a straight normal reference. And just for completeness, well, you might think you could, instead of using regular reflection, you could go use method handles, and that might be an even sneakier way to get hold of this stuff. Well, that won't work either. Same problem. Okay. Let's make a little app, or let's compile a little app that I've already got. Here's a little app. It uses log4j, and it just logs. Okay, I'm starting. Okay, I'm ending. A really trivial thing, but it needs log4j. Now, what I've done here is converted. If I look and I've made a little module library directory. I've converted the log4j core jars into what we call modular jars. So this is a migration path. If you have something that's shipped as a jar, you can add module metadata to it. It can be then be used as a regular jar on the class path, or you can stick it in a module directory and put it on the module path. Module path is like the class path, but it's for modules rather than jar files. So we've got these modular jars in mlib. And wake up. we need to, let's see, we need to compile our application against the log4j API. There we go. Oh, and since this is logging and configuring anything with any kind of logging system requires XML, we need to copy that in. Now, to run this, I'm going to say java-module path mods. Remember that's where the modular jars containing log4j are. Class path. Oh, sorry, actually, this first one should be mlib, module library. Class path mods app, that's where I compiled my app into, and then com.app.main. And sure enough, yes, that works. Okay, now what's going on here that's any different from normal? Well, if I ask the VM nicely, it will show me all the modules being loaded during that to make it work. Oh, and that's not, okay. All right. Now, I can also package the main, this little trivial application up in its own modular jar, and I'll do that with the jar command. Now, if we look in mlib, we have the log4j modules, modular jars, and the app modular jar. And now I can run the application just by pointing to the mlib directory and saying I want you to run the app module and the com.app.main class as its main class. And there we go. Now I can go even further. Let me remove the app jar, and what I'm going to do now is make a JMod. So in order to ship the JDK as modules, modular jar files aren't enough because we need a format that can accommodate native code and configuration files and man pages and all this other stuff. So we're going to define a new format called JMod. You don't have to use it, but it's there. And if you're shipping something that has a bunch of native code, it might be useful. So let me package this guy up. We have a tool, the JLink tool is capable not only of making custom images, but it's also the tool right now we use to make JMod files. Eventually we're going to split that functionality out into a separate tool because we think it'll just be easier to use. So JLink class path mods app format. It's hard to type at this angle, forgive me. Main. Its module ID is app version 1.0. Output mlib app 1.0.jmon. I think that'll work. Oh, dash dash. There we go. Now we have that. So I can now run it. Mlib, and here all I need to say is, go run the module app. When I created the module, the module itself has information saying, well, its main class is com.app main, so that'll just work. And there are the modules that the system configures when it starts up to run this. Okay. Now, if I ask what modules are in this runtime image I've been using, I'll see a lot. Ow! That's not working. Oh well. And that's all. Oh, right, sorry. This bug has been annoying me for a long time, the fact that the launcher's help output always goes to standard error. Arr. Okay, that's easy to read. So there are 55 modules comprising the entire JDK. So let's make a custom image that contains just the log4j modules and nothing else. Module path, the module lib plus, I've defined this mods variable to point to the directory that has all of the JDK JMods in it. Add mods log4j.api and log4j.core, format JImage, output image. Copies a bunch of stuff around. Look at image bin java-x list modules. And there it's got base and the two log4j modules and just the other modules that are needed for the log4j modules. And I can use that to run my little application. Oh, sorry, -m app. There we go. Okay, there are a couple more steps I could show here, but time is running short and I'd like to leave some time for questions. So I will switch back, just for the sake of cleanliness, to here. Maybe. Oh well, it's not that important. So, any questions? That's the end of my story. Feel free to ask a question, or you can tweet it at me, Reinhold, and I'll try to answer it that way. Ooh, and Dan will run around with the mic, so I don't have to. Thank you, Dan.
Hello. What do you think is going to be the future for the jar file system? Which Java version will kill the jar file system?
Jar files will be with us until the heat death of the universe. Jar files will never go away. There's too much code out there. You know, I'm sure long after I retire, long after everyone in this room has retired or gone on to other projects, there will be jar files running. You know, just as there are. You know, today we have COBOL code written in 1963. You know, running large banks. They'll never go away. Don't you? There have been a number of times people have heard me speak about this or read what I've written and said, "Oh no, the sky is falling. Jar files are going away. Everything's going to break." Don't believe them. It's not true. You know, there'll be a new option called JMod. You can use it if you like, but you don't have to.
Question here.
Hi, Kurt.
Hi. I noticed that the ext directory is all going away, and that mechanism is all going away. Excuse me. Can you comment on how that affects the structure of class loaders within the JDK? I imagine the ext class loader is now going away with it.
Good question. So the extension mechanism is going away, but the class loader is not. So as you may recall, since Java 1.2, there's been this hierarchy of class loaders. There's the bootstrap class loader, which loads core system classes. There's the extension class loader, which loads so-called extensions, a poorly thought out mechanism introduced for dubious reasons around 2000. And then there's the application class loader that loads your actual application. The extension class loader won't go away. We're actually going to repurpose it and use it for deprivileged system code. So if code is loaded by the bootstrap loader, it actually gets some magic privileges for whatever reason. And we'd rather not give code those privileges if it doesn't need it. So we're moving a bunch of system code to the extension class loader, and it will be used for that. But the extension directory is going away. The extension class loader will never load any code from outside of the JDK, except, no, it will never load any code from outside the JDK. So we're keeping it for that reason. We're also keeping it for reasons of compatibility. It's a common idiom to examine, to get an object, examine its class, get its class loader, and ask whether its class loader is null, or ask if it's, you know, go up the class loader chain. And if there's, in short, there's existing code out there that will get the class loader, expect the class loader to be the application loader, expect its parent to be the extension class loader, or at least be non-null, and then expect it to be null because null is used to indicate the bootstrap class loader, which is built into the virtual machine. We don't want to break that kind of code. So the class loader hierarchy will still be there. And delegation will appear to work as it always has, although having a module system lets us take some shortcuts and make it much faster.
Yeah, I got a question about package safety and how old legacy code can continue to access possibly internal APIs.
Mm-hmm.
Is there any solution? Can we break the security model?
Yes. Yes, but we're going to make it painful. Okay. So, and to be clear, this access control is not part of the security architecture with the security manager and all that. It's completely unrelated. Think of it more as, just like a private field. Well, you can have, something private within a module. But just as you can use the reflection API to access information in a private field or invoke a private method, if you wish, you can go to some trouble, use the reflection API, and do it that way. Or if you're running a bunch of code which you cannot change because somebody else wrote it, you can actually start up the VM and indicate to it, okay, I know I have to, I know I've got this bad code, but help me out here, and allow this module to access the guts of that module, even though it says it's not supposed to. And it's all, dash XX colon, it's ugly and it's intentionally so, but it's possible.
Okay, I think that will be the end of question because we're running out of time. Next session will be here at 2 o'clock, 10 minutes. And thanks a lot, Mark.
All right, thank you. Oh, if you have further questions, I'll be at the Oracle booth during the next break. You can stop by there.